Hey guys, this is the second video for Chapter 8, Hypothesis Testing. In this video, I'm going to be covering a claim or hypothesis tests regarding a population proportion. Some notation that you have to know. So there's a notation that looks like this. This is the p-value, and it represents the probability of the result. There's this alpha, which represents the significance level. These two notation you should have been introduced to before. So p, lowercase p is the population proportion. This is the sample proportion. And then these two you should have been already familiar with. These two are very important as well. This is the null hypothesis, H0 or H sub 0. Or you might hear me say H naught. H sub 1 is the alternative hypothesis. All right. So the first question is, what is a hypothesis test? So a hypothesis test is a procedure for testing a claim about a population parameter, right? We're going to be the general overview of the hypothesis test is very similar to the criminal justice analogy that I showed or I explained in the last video. So number one, we have a claim, right? Step two, we're going to test the claim, which involves additional steps, like determining the null hypothesis and the alternative hypothesis. Step two is we collect evidence, and in hypothesis tests, we collect evidence by collecting sample data, and then we perform a hypothesis test. And there's two methods. We have the p-value method and the critical value method. In this video, we're only going to cover the p-value method. And then finally, step three is we're going to make a conclusion addressing the claim. All right, so I'll walk you guys through this with this problem right here. Just kind of take note, these are the functions on the calculator, the TI-84 that we're going to be using. So this problem says a clinical trial was conducted to test the effectiveness of a drug to treat patients infected with a certain virus. Among 158 patients who received the drug, 114 recovered from their virus. So those 158 patients taking the drug in the clinical trial, 114 of them recovered. Use a 0.01 significance level. So this is my alpha. To test the claim that the proportion of patients who recover from the virus after receiving the drug is greater than 64%. 64% is the percentage of patients who recover from the virus without any treatment, right? So step one is we need to identify the claim in symbolic form, in math form, right? So this problem is involving a proportion. Now, how do I know this is involving a proportion? Because we're looking at a part of a whole, right? Anytime you're looking at a part of a whole, that's what a proportion is. It's a portion of a total or a population or a sample, right? So this is my part, this is my whole. So because it's involving a proportion, our claim would contain lowercase p, the population proportion. And p, lowercase p in this case, represents the population proportion of those who recover from the virus, the proportion of those who recover from the virus, right, out of the population. And what we're saying is that it would be greater than, the claim is saying that it would be greater than 64%, so 0.64, which is 64% as a decimal. All right, so that's our claim. Now we got to test the claim. So we know there's two hypotheses, two outcome, and in layman's term, the first the first hypothesis, the null hypothesis, is that it doesn't work, right? We have to be very careful with these drugs, and we have to assume that it doesn't work. The null is what we always assume to be true, sort of like we assume that a person is not guilty. So that's our null hypothesis, that it doesn't work, but we have to state it in math form, in symbolic form. So in other words, here's what it is. P, the proportion of those who recover, is equal to 0.64, which is 64%. So we're saying that those who take the drug, the recovery rate is going to be the same as for those who didn't have any treatment. So in other words, it just doesn't work, right? It didn't work. The alternative would be what we're trying to prove. So in this case, because we're trying to prove that, that it is effective, then we're going to choose that as our alternative. So P is greater than 0.64. Now, if you didn't understand that, this explanation, um, I have a handy chart that kind of just, if you follow that, it's going to give you the right answer. So I'll show you that in a bit, but just remember the null always says that there's no change, there's no effect, there's no difference with whatever we're trying to test. So in this case, we're trying to test the effectiveness of this drug. There's no change, there's no difference. That's what the null is saying. The alternative says there is a change, there is an effect. And because the claim says that the effective is that the effect is that it's greater than 0.64, 64%, that's going to be our alternative. That's what we're going to try to show. Okay, so if you don't understand that, here's a chart that kind of just tells you how to find it. So the null always has an equal sign. The alternative has these signs depending on what the claim is. So if the claim is less than, greater than, not equal to, then the alternative would be the same as the claim. Less than, greater than, not equal to. If the claim has an equal sign, then the alternative, the sign for the alternative would be not equal. So if you follow this table, you would be good. So again, the notation here stays the same, right? The notation is population proportion. And these numbers stay the same, right? The 64%, that's kind of like our point of comparison. The null is always equal. The alternative in this case is greater than because the claim is greater than. All right. So let me give you guys a big picture of what's going on. So we have a population. The population we're interested is those who have been infected with this virus, right? And there are currently a lot of people, right? Millions of people. I think currently, let's say there's like 2 million people infected with the virus. And we're interested in P, and P represents the population proportion of those who recover from the virus. And we're trying to see if this drug is effective, right? But it's unethical to give everyone infected with this virus the drug, right? What if the drug actually does worse things? So we conduct a clinical trial, or a clinical trial was conducted, which consists of 158 patients. And of those 158 patients, 114 of them recovered. Now, we can calculate the proportion of the sample that recovered. So that notation is p hat. So p hat is equal to x over n, right? 114 over 158. And that's going to be approximately, so let's pull this out, pull out the calculator. That's going to be 114 divided by 158, which is approximately 0.722 or 72.2%. So 72.2% of the sample, the 158 patients recovered. Now you might say, well, 72.2%, that's better than the 64%. So shouldn't we just conclude and support the alternative that P, the proportion of those who recover, is greater than 64%? Well, not so fast, because this is only a sample of 158 patients who were infected. There's 2 million people who are infected, right? So we have to test, well, do we just get this by luck? What are the chances of this occurring, that this drug, the drug resulted in 72.2% of the patients being recovering. So what are the chances of that? So we're going to find two values. For that, we need to calculate two values. We need to calculate the test statistic and the p-value. So the test statistics can be thought of like the z-score of the result. The z-score, if you guys remember, z-score is like the number of standard deviations away a value is from the mean. So the higher the z-score or the lower the z-score, the more extreme it is, right? Um, and we also need to calculate p-value. And p-value, you can think of that as the probability of the result occurring, assuming that the null hypothesis is true. Again, p-value actually is more complicated than that. You can look at the definition, but for now, it's good enough to think of the p-value as the probability of the result, assuming that the null is true. All right, so for this, we're going to use, because we're involving we're conducting a hypothesis test for a proportion, we're going to use a function called 1-prop-z test on our TI-84 calculator. So let me go ahead and show you guys where that's located. So we're going to click stat, and we're going to go to tests, and we're going to go to 1-prop-z test. And I already have it entered, right? So P0 or P naught is the value that's in the claim. It's always a value in the claim, so that's going to be 0.64. X is 114, right? Those in the sample that recovered. N is our sample size, 158. This next line right here, this is the alternative, the sign in the alternative hypothesis. So the sign in the alternative, H1, is greater than. So we're going to choose this. So we're going to navigate to this and press enter. I already have it selected, but if you didn't have it, you'd navigate to the greater than sign and then press enter. And then we're going to calculate. So the result here, the output, the first line here is this is just showing the alternative. So the alternative is that the proportion, is greater than 0.64, right? That's our alternative right here. The proportion is greater than 0.64. The z here, the second output, this is our test statistic. So our test statistic is 2.13, right? We're rounding to 2 decimal places here, which is, pretty extreme, but we'll see. Is it extreme enough? Well, we'll see. The P here, do not confuse this P right here with this one. This is the population proportion. This P right here is actually the p-value, the probability of the result, assuming that the null is true. All right, and that is 0.0164. Now, this is the probability of the result, of getting this result, assuming that this was true. Now, is this probability low enough to where we would say that this result probably didn't happen by chance, right? Getting this proportion that's higher than the 64% probably didn't happen by chance, so it must mean that this drug is effective. Is it low enough? Is this probability low enough? And how do we know when it's low enough, right? So we know probability ranges from 0 to 1. We know that as we get closer and closer to 0, that the probability, the chances of that event occurring is unlikely, right? 0 means it's impossible. But is this probability low enough to where we can say this didn't happen by chance, right? Getting this proportion, this high proportion, didn't happen by chance. Well, for that, we have to look at our cutoff point is alpha, our significance level. So in this case, our significance level is 0.01. So this is our cutoff point. And what we're saying is that any event or any result with the probability of 0.01 or below would be considered very unlikely, such that the result that we get is probably didn't happen by chance. In other words, we didn't get lucky that we had this result, which is bigger than the 64%, that there is something going on where the drug is effective in this case. Well, now let's compare our p-value. So in other words, we're going to compare our p-value to alpha. So the p-value is 0.0164 and alpha is 0.01. And if the p-value is less than alpha, if the probability is less than our cutoff point, 0.01, then we reject the null, right? We assume the null to be true, but we're going to reject it. If the p-value is greater than alpha, then we're going to fail to reject. Well, in this case, the p-value is actually greater than alpha. So the p-value is greater than alpha. So in other words, we're saying that it's the probability of this result is not low enough to where we're comfortable saying that it is effective. So the p-value falls like right above the alpha 0.01. So we're going to fail to reject the null. Now, I want to warn you guys, the significance level for each problem is always going to change. And in real life, it usually you want a lower significance level if the ramification of what you're doing is more important. So for something as important as a drug, for like a virus, you want your significance level to be low because you want to have such a high bar to where the probability has to be so low that it didn't occur by random chance, right? And so in this case, we fail to reject the null, right? We assume the null to be true. The null says that there's no effect, but we're failing to reject the null. Since the p-value is greater than the significance, so greater than the significance level. All right, so hopefully that makes sense. So we fail to reject the null. So in other words, we're not rejecting it, which means we're in some ways, I'm going to put in quotations, we're going to support it, right? Because we're not rejecting it and we're not supporting the alternative. Now, you might say, well, why couldn't we just say we accept the null hypothesis? Isn't that the same as fail to reject? Well, it's not the same. It's sort of like why we don't say someone is innocent if a jury doesn't convict them. If the jury says not guilty, we're not saying that the person is innocent. We're just saying that there wasn't enough evidence to show beyond a reasonable doubt that the person did do it. They could have done it. So we say they're not guilty as opposed to we're saying that they're innocent. So kind of like the same deal here. We're going to fail to reject it as opposed to accept the null hypothesis. All right. And finally, there is blank evidence. So there is not sufficient evidence. There is not sufficient evidence to support the claim that the proportion of patients who recover from the virus after receiving the drug is greater than 64%. So the final conclusion always involves two things. It involves a statement about the null hypothesis. Why the null? It's because we assume the null to be true, so we have to address that part, right? So we're going to either reject the null hypothesis or fail to reject the null hypothesis. And it also involves addressing the claim. So in this case, there is not sufficient evidence to support the claim, right? We're supporting the null hypothesis, which says there's no effect, and we're not supporting the alternative, and the alternative happens to be the same as the claim in this problem. Not always the case that the claim and the alternative is the same, but in this problem, it is the same. So hopefully that makes sense. Let's go ahead and take a look at another problem. Just, repetition is a key, right? Before I take off to the other problem, you're probably wondering, like, how do I choose all this stuff? So in this page, your page of notes here, or in your notes, this tells you when to reject and when to fail to reject, right? If the p-value is less than alpha, you reject. If the p-value is greater than alpha, we fail to reject. A saying that we have in statistics to kind of help you remember that is, if the p is low, reject the null, right? And then if you reject the null, then there is sufficient evidence. If you fail to reject the null, then there is not sufficient evidence. There's a lot more to this, but this is like this is the simplified, um, you know, way to go about it. So reject the null, there is sufficient evidence. Fail to reject, there is not sufficient evidence. So if you understood these two parts, you should be good in figuring out the final part, the final conclusion. All right, so let's go ahead and go to the next problem. So in this problem, we have, this is the M&M problem. It says, according to Mars Candy Inc., which is the company that makes M&Ms, the distribution of colors in a bag of M&M plain is 13% brown, 14% yellow, 13% red, 20% orange, 16% green, and 24% blue. A self-proclaimed candy connoisseur claims that the proportion of green M&Ms is less than 16%. He buys several bags of M&Ms, and out of the 1,680 M&Ms, 251 of them are green. So that's a sample that he's kind of using to prove his point. Use the sample data in a 0.10 significance level to test his claim. So the significance level in this case is a little higher because this, it's just M&Ms. It's nothing that's super important. So the less important, you usually want to just kind of boost up the significance level. All right, so let's conduct a hypothesis test on this, on this problem, this situation. So again, this is a proportion because this is involving a part of a whole, right? Proportion, part of a whole, a proportion. And another big hint is whenever we're working with percentages, like the claim involves a percentage, percentage is just another form of writing a proportion. So this is a proportion. Now, how does that help us? Well, we know that the claim is going to contain P. The alternative in the null also is going to contain the notation P. P represents the population proportion. And the claim is that the proportion of green M&Ms, so P here represents the population proportion of green M&Ms, is less than 16%. So as a decimal, that's 0.16. So the null says that there's that there's no change or like no difference, or it's sort of saying like everything's still the same, right? The proportion of green M&Ms is 16%. There hasn't been any change. It's still 16%. That's essentially what it's saying. And if you don't remember that, if you don't remember how I got that, just remember the null always has the equal sign. Okay, and then the alternative says, well, there is a difference, that the Mars candy is being dishonest, or their distribution is not correct, that there is a difference. It's not 16%. And because the claim is saying that it's less than, we're going to adopt that as our alternative, right? All right, so now we have to figure out the test statistic and the p-value. And for that, we're going to use one prob z test. So let's go to our calculator. So stat test, one prob z test, and p naught, p0 is always the value that's in the claim. So that's going to be 0.16. X is in our sample, the 251, which are green, and then N is the total number of M&Ms in our sample, which is the 1680. And this next line is our alternative. The sign of the alternative is less than. So we're going to calculate, and there it is. So our test statistic is negative 1.18, which is rounded to 2 decimal places. And our p-value, this p here is our p-value, right? Not to be confused with the population proportion. This p right here is the p-value, and that's approximately 0.1181, rounded to 4 decimal places. So here's, again, let me give you guys the overall picture of what's going on. So we have this population of M&Ms, and there's millions and millions, right? And P here represents the proportion of the population proportion of green M&Ms, right? But it would be silly to get to check the entire population, count all the green M&Ms. So we take a sample, right? So this food connoisseur takes a sample that consists of 1,680 M&Ms, and of those, 251 are green, which makes p hat, the sample proportion, equal to, so that's x over n, right? So let's go ahead and calculate that. So that's going to be, actually it calculates it right here. So p hat is 0.149, 0.149. So approximately 0.149, which is 14.9%. Now you might say, well, 14.9% is less than 16%. So does that prove our point? Does that prove the food connoisseur's point? Well, we can't say that yet because this was just a sample. Maybe he just got lucky, right? So we have to look at the probability of getting this result. So the probability is 0.1181. Is that a low enough probability where we can say that this didn't occur by random chance? That wait a minute, maybe there are like significantly less green M&Ms, less than the 16% that the company promised. Well, to um, to see if it's low enough, to see if this probability is low enough, we're going to compare it with alpha, which is our kind of our threshold, right? So p-value is 0.1181, alpha is 0.10. Well, the p-value is greater than that. So in other words, the probability of this result is not low enough. It's not lower than our threshold of 0.10 to where we can say that it didn't happen by chance. So maybe we just got lucky because the probability wasn't that low. So if you remember, going back to our notes, whenever the p is greater than alpha, we fail to reject. So in this case, we're going to fail to reject the null, right? We always assume the null to be true, so we have to address it. We either have to reject it or fail to reject. In this case, we're going to fail to reject it, which means in a kind of backwards way, we're going to support it, or we're going to side with this, right? Which means we're not going to support the alternative. Okay, so we failed to reject the null since the p-value is greater than the significance level. There is not sufficient evidence. There is not sufficient evidence to support the claim that the proportion of green M&Ms is less than 16%, right? So the claim says is less than. We're supporting the statement that says that the proportion is equal to 16%, and we're not supporting the alternative, which says that the p is less than 16%. And again, the null and the alternative and the claim happens to be the same. So, and we're not supporting the alternative, so there's not sufficient evidence. Now, you might say, well, when is it low enough? So let's pretend instead of getting the 251, let's say that you know, he actually got maybe like 139 or something green M&Ms. Let's see what happens. What would happen in that case? How would that change the p-value? Would the p-value be less than? Or I'm sorry, would the p-value be smaller than this p-value? Well, let's see. So we're going to go to stat, calc tests, one prop z tests, and we're going to change the 251 to 139. And everything stays the same, right? So we're going to calculate. And now, see how the p-value is practically zero. The chances of getting 139 out of 1680 is so low. So again, assuming that the null is true, that the proportion of green M&Ms is 16%, the chances of getting 139 out of 1680, which is about 8%, right? P hat is 8%. If you do 139 divided by 1680, that's 8%. To get 8%, that low of a amount of green M&Ms is so low that the probability is practically zero, that it probably didn't happen by chance. Getting this much low of a number of green M&Ms probably didn't happen by chance. So in that case, all of this would change, right? We would reject the null that says that it is equal to 16%. We would reject that statement, which we assume to be true initially, since the p-value is less than the significance level. And then there is sufficient evidence to support the claim, had this been true, if it was 139 out of 1680 that were green. So hopefully that makes sense. If it doesn't, you can always shoot me an email, work out your homework problem, and good luck.